In our room, we are having about 6, maybe. Yeah, 7 lights. And we are able to have these lights because of electromagnetic induction. You were complaining of the first sections, the abstract, where we're going to use them. Here we are living with electromagnetic induction. You are able to have this fun run because of electromagnetic induction. You put in a current, it produces a field, and the field makes the conductor rotate, and then you are able to enjoy the free air. The ingenuity of the person who saw that when you have a conductor in a magnetic field, the force acts on it, was able to integrate it with a couple of blades, and then was able to give us some fresh air. And that's why I was telling you that I don't have to teach you this and say you can do this. So today I've made sure that I share with you one of my treasures, one of my collections of my richness, which is a torch, a radio, and a siren. And all you need is to have a couple of food, eat it, and then make it run. So I will see whether I can make some light come over to you. Well, I will first switch on. I think it will die out in a little while. It has a battery inside the conductor. So as I turn it, I will try to produce some electricity. We should be able to increase as I turn it. I can assure you, by the time you make it, light for about more than 30 minutes after you have done it. It's a hassle, but you can imagine if you were like in the night or a cold night and you still need light, it should give you some sense of doing an exercise. You can do it and get the light as well as do some exercise. So this is the beauty of the person who made this. Was not told that make this after learning electromagnetism or electricity and magnetism. And I don't believe I don't remember whether I shared with you this thing by the time, because I think I shared with a group of the other year. No, you. Then of course it has a siren. So in case I'm in the jam and I'm scared, I only need to charge it up, and I will scare all the drivers around by chasing them away. So if it is somehow in the night, I can charge it up before I go. So when I reach the jam, I scare them. That's one more thing. Also, it can help you to be identified. If you were like you have round on the lake, it can help you to be, to be seen where you are. It can act as a signal or whatever you are. The last thing on it is what all of you would like to have when you are bored. The radio. I did not make it, but the Kavos is the first one. So it's a digital radio. It's a digital radio, so you just scan. So and Kavos is the first one. So, but I did not want it to say Kavos. So you really like to have a program, like you want to have a radio program. It's a talk show, and it's starting at 7. You can have some exercise around, and then once you are done, you put on your radio. Whether we can listen for some time. So now you appreciate Now you appreciate that actually we learn stuff in the... We should appreciate the kind of science we study has applications. But just because we live in this remote area of the world, and because we don't even know whether these things are there, we say it's not happening. Before you were interfaced with this machine, you couldn't believe that putting a finger on a given surface can lead to a message saying thank you or try again. So you have, if you are doing electronics and instrumentation, it gives you an idea of what we mean by input devices. You input your fingerprint, a message is sent to the electronics configuration, it interprets your finger and sends a message of what should come out. Either thank you, or if it is the actual signature on the fingerprint, or it says try again if it is not. So whatever you'll be able to do in the future from the course or from whatever I teach you will depend entirely on your ingenuity and your exposure. You can never say honey is sweet if you have never eaten honey. Can you? I don't know how booze tastes, so I don't know whether it is nice or not. So I can't say anything, and it will die out slowly when the water charge goes away. It has a battery. If I can do it for a whole day, maybe I can enjoy 5 hours of listening after doing it for the whole day non-stop. I'm looking at, and you can imagine if there was a way, and that's how the car works. The battery of the car only helps on igniting the car. Once you start moving, the dynamo, which they sometimes call alternators, is the one which produces electricity. That's why you will find people blasting music because they are not worried. The electricity is already produced as long as the engine is running. Okay, so I believe I have tried to use 1% of stimulating your minds. And I have to check. I bought it in 2.7 on the internet, and they sent it to me. So you saw me that without having emotion, okay, without making any motion, there's nothing that could have happened. And all this principle came out of Faraday's experiments. He did an experiment, and first of all, he got the first one was to get a coil and connect it to the Sena zero galvanometer, and then he used the magnet with the north, of course, whose field lines would be moving out like that, and then had to move a magnet, have relative motion. And when that happened, the galvanometer was able to have a kick. You know, you could see something making a kick. At the same time, when he saw step 1, the magnet was moved. Step 2, the magnet was left stationary, and then the coil was moved. And still there was a kick in on the galvanometer. The third one, he tried to change the magnetic field. So assuming instead of the magnet, you have another supplier of the magnetic field, like the Helmholtz coils or any other electromagnet that you can change its magnetic strength. You also saw that when you try to change the magnetic field, then there is also a kick in the galvanometer, a kick which is brought about by the induced EMF that produces the current flow, and when the current flows, you get the kick or the motion. And of course, this is the principle. I mean, the galvanometer is the principle. If you remember the moving coil galvanometer, where you have, you know, the coils, the coil on the frame, and then you have your J-rings, and also at the bottom here, and you have the hair springs, and then you have another hair spring which goes to the wherever you are supplying the current from, and then you have your pointer, and this pointer is on a scale. So by Fleming's left-hand rule, if the current was flowing to come and flow down here, and inside the other side it was to flow upwards. So if I am on this one, second finger is current, first finger field, M motion, thumb motion. So I have the current, I have the field. So if we had our concave whole piece magnets, and for example, if I'm like this, the field. So let's say this is our north. So as Faraday was coming up with nice E proportional to the phi dt, Lenz said, okay, it is opposite to the change positive. Whatever induced EMF that makes the current to flow, will make it flow in a form as to oppose the change positive. So, any questions so far? Any feelings about electromagnetic induction? Yes? I repeat the left-hand rule. So this is the coil. And then I have the J-rings here. And I have the J-ring is just it's like a support where this axis, which holds the coil that can turn comfortably. That's what we mean by metal J-rings. Stay in a place where it's like a notch where it sits. And then there are hair springs to make sure that they can always, it turns easily. If you put strong springs, you will consume energy in just turning the coil instead of measuring the energy. So you can imagine you want to measure the EMF of the dry cell, and instead you are consuming the dry cell, but you are saying I'm measuring. So if the current is moving up there and moving down here, and we have a field because it is north to south, I want you to learn that you can just have your finger and then all of a sudden you can make them go 90. No, I have those who do like this. They even try to stretch their hand to make it. So now, for AB, I will have the current upwards. I have the field this side, and then that means the force is into the blackboard. If I come on this side, the current is down, the field is still this side, the force is coming out of the blackboard. Typical couple, equal but opposite, and then you have a turn. And of course, the pointer will be moving in this direction. If I wanted to follow the actual of this being 0 and this one, and wanting to be a clockwise, then I should have done that, and this current would be downwards. And then I will be able to say this is the current field, so the force is in that direction. This would be force this way, and here the force comes out this way, and then I would have the pointer moving the clockwise direction, measuring from 0 if I haven't put any current, and increasing depending on the amount of current I'm making flow. Is it okay? So Faraday's law Faraday's law is in 1831. A one microfaraday reported on a series of experiments. Including three that with some violence to history, can be characterized as follows. Okay, so in experiment 1, so I'm going to draw the different scenarios here, so that as we write about them, you know when to draw them and how they look like. So the first scenario, this box here shows a region with a magnetic field, okay? So this is a region of magnetic field. So the second scenario, we have the current flowing in this part as well. But this time, if you move the field itself, okay? So like when I drew the coil, we could have moved the magnet henceforth, or we could move the coil itself. Okay? So I drew here a diagram or a picture, but this is a schematic. So this is B, and this is B. And the one now which is moving is the field, and this is the velocity field. And the last one, and Bob, if they give me an opportunity to be in charge for just one day, I can make all the believers count, give a friend or three next time.
But in chess, they don't give
Is what?
They don't give an invitation, they just put as a believer.
So here, if we have our eye again, and instead we only have a change in magnetic field. So I will write it somewhere that this is change. I think it's nice to point around this way. Change in magnetic field. So, for example, if you had two Helmholtz coils, did you work with Helmholtz coils in second year? So, or first year? You asked me, you are the one who told us, why did you do it? So if you have Helmholtz coils are two coils whose distance between them is the same as their radius, and they are identical. And they are used to always produce uniform magnetic field in between them. So the scenario I'm talking about is if now we moved the coil in here, we'll get a kick. Now if we move the Helmholtz coils with the coil static, then we would also get a kick. That is the second experiment. The third experiment is if we varied using a rheostat, if we varied the current within the coils, the Helmholtz coils produce a magnetic field changing within where our coil is, then also the kick was registered in the galvanometer. Those are the scenarios we are talking about. So I'm going to now write them here. I'll put one here, then put the two somewhere, and then we draw these scenarios finally. I'm just doing this to give you an insight, a revision of what we did in electricity and magnetism, but more interested. You know that none of, even myself, until when I started teaching this course, that I knew that Faraday had another name called Michael. In Europe, most courses, the lecturer starts by giving a historical development of the course. Who invented this? By what? What time? You know, we have gone through a series of things. This one discovered this one discovered this. Newton said this, Einstein said this. You know, who else? Okay, so we have that Faraday pulled a loop of wire to the right, pulled a loop of wire to the right through a magnetic field, and this is as in figure A. A current flowed. I hope that is grammar. That grammar is okay. A current flowed in the loop. That was experiment 1. He pulled the V here shows the velocity, the speed. So he pulled with this whole area being infested with the magnetic field. He pulled the loop to the right, and then he was able to register a current flowing through it. It's not magic. You can register that by using this, but we cannot draw all this in one diagram. I say this is a schematic. This is actual thing that would have happened. Experiment 2, if I can, or maybe I put experiment 2. He moved the magnet. So we're talking of moving the magnetic field, a field that is having magnetic force, to the left, holding the loop still, holding the loop static or still. That is figure B. Again, he was able to register a current in the loop. So for part 2, or for figure B, he now moved the magnet away, and then he was able to get the current flow in the loop as well. Then experiment 3. Experiment 3. With both the loop and the magnet at rest, which is in figure C, he changed the strength. He changed the strength of the field. Change the strength of the field, and we say that for this case he had used. He used an electromagnet, he used an electromagnet and varied the current in the coil. When I say in the coil, remember we are using the loop to mean this part here. But the coil we are talking about is like this coil of the Helmholtz coils, whereby we are using this setup as our electromagnet. So when we say he now made the magnet and the loop, the magnet we are talking about now is an electromagnet whose strength can be changed by varying the current flowing in the coil. Once again, when he did that, once again, current flowed in the loop. Of course, when you do an experiment, you have some conclusions out of your experiment. So now you can draw those parts. An induced current is produced when there is relative motion. Relative meaning that it is either the magnet or the coil or the loop. It is either the loop or the magnet that has to move in order to have an induced EMF. So the second note is that the magnitude of induced EMF, which results into a flow of current, is proportional to not only the magnetic strength, but the time rate of change of the magnetic flux. And this phenomenon which we have just been playing around with the phenomenon of when these things happen is called electromagnetic induction. So, I think this would be a nice and appropriate moment to hang on, so that our Thursday can help us to complete this section. So the induced EMF is given by from the notes we wrote down, we say that induced current is produced when there is relative motion. That was general in a sense. 2, we said the magnitude of the induced EMF or the current which results from the EMF is proportional not only to the magnetic strength but the time rate of the change of the magnetic flux. Meaning that if we can write this, we shall say that the nice E, which is induced EMF, so I can stop on E induced, is proportional. So it is proportional to the time rate of the flux linking the coil. And of course, from lengths, the direction of induced EMF, the direction of induced EMF is such that the magnetic flux associated with the current generated by it, that it means induced EMF, opposes the original change of flux, causing the EMF. Thus, we can say that the E induced, or the induced EMF, is equal to d phi dt, but in order to express the opposingness, then we put a negative in here. And we shall preferably call this one equation 1. In SI units, in standard international units, which you are used to saying SI units, constant of proportionality is found to be unity. So unity, I'm talking about, when I say unity, I mean one. Okay? So the induced EMF is often called this is sometimes called, because it opposes, we call it back EMF. And this is always the problem, although we shall not cover this. This is always a problem in electric motors. That as you apply the current, like in an electric shaver, as you apply the current to make the shaver, I don't remember what I explained about how the shaver works. The shaver, the one at least I have used, has a motor. How many of you have ever opened the radio cassette? So this motor moves inside here, and then in the motor, assuming this is the motor, towards the end of the motor, or the edge of the circular motor, like at the end, there is something protruding out. So as the motor turns, this thing is also turning. So it is turning at the end of it's like it is on the end of the circle. Now what happens is this motor hooks on a part of this one which has the teeth. Okay? So if you remember in your simple harmonic motion, whereby when you draw a circle and you draw the diameter and you take a given point moving around the circle to be casting the shadow on the diameter, and this is the origin. So you are having the shadow of this. So take for example my box to be like the one casting the shadow. as I swing my box, every time if it is here, the box is casting a shadow on the center, it is casting it here, at the end it will be again going again. If you are going to have a shadow coming from down, it will again be going here. So you'll have my shadow oscillating on the diameter. And that's when we say that eventually you have something oscillating. But the box is continuing to move around. So as that thing goes around, it keeps pushing the one side of the blades over the side of the fixed. So this is fixed, and this is well moving. So so that's how the simple amount motion used to happen. So normally what happens in electric motors, like the one which I'm trying to explain in the shaver, when you apply the current, that current also produces a field. This field also induces an EMF. And this EMF it is producing is opposing the current that caused it. So you find that your battery is able to get used up, or actually your electricity, you use a lot of electric bill because you are having this car that uses a lot of electricity, because even what it is producing is causing it to oppose it. I have a video lecture where I should share with you one evening, showing you how the eddy currents work and why, you know, if you have a ring, like an aluminium ring, and you make it go through the magnetic field, like of a Helmholtz coil, if it is complete, it gets dampened, but if you slice it up, it will go through quickly. Because there is no current that will be induced, it needs to cause an eddy current. That's why in electricity and magnetism, I should have brought you here, I think, a transformer, and showed you the E iron pieces which make up the soft iron core that transmits from the primary to the secondary. Because the change in magnetic field in the primary transfers the soft iron core transfers the magnetic field, or which becomes flux to the secondary, and depending on the amount of, depending on which one you want, whether a step down or a step up, then that current of the magnetic field produces. So the primary and the secondary are not connected. There is no current connecting the primary of the transformer and the secondary of the transformer. It is only the field that crosses, and when it cuts across the coil, the windings in the secondary, then you produce a current. If the primary windings are more than the secondary windings, you get a step down. If you get the primary being less than the secondary, you get a step up. So I now have successfully reminded you what back EMF is all about. So in electromagnetic fields, which are conservative, the field is conservative, implying that the integral over the closed surface, either the air, is null or is zero. This is when we have conservative fields. But if we have time varying fields, for time varying fields whereby, after a while they change, then we have that, not time varying, they're time varying, so maybe I just grab this and in brackets, time dependent. Time dependent fields. In the notes it is time varying. So we can say if they depend on time. That is, they vary with time, if they are time dependent. Then we have that the induced EMF is equal to integral E dot How about if we consider a surface which could be arbitrary? What would happen to our induced EMF in such a within a given surface? Consider a circuit C enclosing the surface S, placed in a magnetic field B. Placed in a magnetic field B. So I'm having a circuit. I'm just drawing it to show that it is horizontal, otherwise it's a circle. And then let's take these fields going through, and we shall take one of the fields and take a normal to this field to be N roof. Then we have, I think we can do that. And this is the whole surface S, and this is the circuit C. We take this to be along the length of the circuit, so this is dl, and we take E along this part. Now take a small element. I think this is our small element. Take a small element, ds, whereby n being a unit vector a normal unit vector, I say unit vector normal to a unit vector normal to the surface. So we can expound on this and say that the flux phi, you know better, is the magnetic flux density. Magnetic flux density, or the magnetic field lines, or if we were talking about the EDS for the Gauss's law, the integral theta ds being the same as the total charge enclosed over the permittivity. So instead of making somebody wonder what is if this was to be a perpendicular surface, we prefer doing this to make our life easier. So this would be the same as integral over S b dot ds. Now that you know, since n ds is equal to ds, and we should call this one equation 3. So according to Faraday's law, E induced is equal to integral A dot dl, which is equal to, I should have said, well, it is nice. According to Faraday's law, this induced EMF should be equivalently, or should also be equivalent to this, and Faraday's law is the same as, taking care of Lenz's observations. d phi dt. And we can write this one as equal to, substituting for phi, where is phi here? We will get that this is minus d dt integral b dot n ds. So we have substituted for phi. Now the time derivative is independent of the path of integration. We don't care where we are going as long as we are integrating, we are differentiating with respect to time. The ddt doesn't care where you are moving to. And if that is the case, because as long as I'm interested in time, I don't care whether I'm going this way or this way. Whether you are going to your hall of residence, time will move. Whether you are going to Chikoni, time will move. Whether you are coming from Chikoni, time will move. Okay? We determine this, that the time derivative is independent of the path of integration, and for that reason, this would imply that E induced is equal to integral E dot dl, which is equal to minus integral Kali B by Kali T dot n. Yes, we would have that the integral over the closed circuit dot dl should be equal to minus integral over the surface S Kali B by Kali T dot, let's now write it as the vector yes, because we are not going to be confused at this moment. We've already rectified the issue on how it comes about. And this is our equation 4. And it is of significant importance, and its name is that this is the integral form. This is the integral form of Faraday's law. Faraday's law. Integral form of Faraday's law. So from Stokes' theorem, I will say that the integral E dot dl, I can transform it into a surface. And then I will take a curl of the vector and then dot it with a surface. So that this will be the same as integral the curl of E, and then I dot it with S. And this would imply that the integral over the surface S, the curl of E, then M ds is equal to minus integral S Kali B by Kali T dot N ds, and this is equation 5. Now for some surface S, in other words, if you say that for an arbitrary surface, for any surface, we don't care about the dimensions, we don't care about how it looks like. The integrand means what you are integrating. The integrands are equal. If we are trying now to integrate over the surface both sides, then that means these ones, if these two are equal, then the integrands are equal, implying that the curl of E should be equal to minus Kali D by Kali T. So the curl of E is equal to minus Kali D by Kali T. So when you try to curl the magnetic fields for any surface, you want to make them curl around. This would, in relation to the magnetic field that they were producing, these fields would have been producing, the electric fields would be producing, you will be reducing them. Yes?
Does it stand for the
Electric field intensity. I believe we are in, first of all, we are in time varied fields. Okay? The other time we were having the electrostatic fields. We are having a unit charge producing a field. And when you have this charge constantly producing one coulomb, it will be having its fields and they are straight and they are pointed to a given direction. And that's why trying to curl them was a problem. But here we are having time varying electric fields. And when you try to curl them, actually, the rate at which the magnetic field is changing, it changes negatively, considering how you are trying to curl this change in magnetic field. So here we are having time varying, time dependent fields. The curl we got in the previous section is because we were having studied. You put a point charge, or you put an amount of charge, and then it gives you a field. If you try to interfere with it, you get problems. And of course, this equation 6 is the opposite of equation 4, and this is the differential form. Equation 6 is the differential form of Faraday's law. Okay, so now we have tried to socialize with Faraday. Now let's move on and see how about if we get concerned with the vector potentials in varying magnetic fields. We already have seen the magnetic vector potential in the non-time varying fields, right? How about in when we have time varying fields? So, as a subheading or subsection, vector potential in a varying, of course it is only one vector potential, A, in a varying, is it in a varying or we say invariant? Invariant magnetic fields. So I remove the A here and make them fields. Or you want it to be a varying magnetic field? Yes. Okay, that sounds better. Haven't I been democratic? So Faraday's law in differential form. Faraday's law in differential form. We have that the curl of E is equal to minus Kali D by Kali T. And then we know that previously we said that B is equal to the curl of the vector potential A, implying that now our curl of E will be equal to the minus Kali D by Kali T, the curl of A. So this would imply that the curl if I take this one this side, I'll get the curl of E plus curl, because I can take the curl out, the curl, or the gross product, I mean not the curl, but the gross product of the sum of two vectors is it distributive or associative? I think it is distributive. And this would be curl A by curl T, and the other side would remain with a 0. Now, using the vector identity, I believe a bunch of you have those vector identities still, which we used in the test. So, using the vector identity, the curl of minus grad phi is equal to 0. So if we had a minus grad phi inside equal to 0, then we can say now that if we replace this one inside here with minus grad phi, where phi is any vector, any scalar potential. So if we follow this identity, then we shall have that this implies that whatever was here, if we compare it with this identity, then we shall say that the E plus the curl of A, the curl A by curl T, or the partial rate of change of the vector potential is equal to minus grad scalar potential, where phi is the electrostatic which we normally call the scalar potential. If you go in Schum series, they are kind of pamphlets. They are like pamphlets. They have nice diagrams. They are in classical mechanics. There are some for, I'm not sure which one, but they are more in classical mechanics and vector calculus. They are Schum series. They are books called Schum series. They have nice demonstration. Nice diagrams of 3 dimensions. Some questions of in mechanics. It's nice when you read them to understand these principles of vector analysis in terms of the dot product, the cross product measurement. So finally, we can say that the electric field intensity is the same as minus grad phi minus curl A by curl T, and this is the case, the nature of our electric field intensity in terms of the scalar potential and the magnetic vector potential, where you have a magnetic field and you have the potential, the electric field intensity in this kind of time varying fields, you get it as this for time varying fields. We, however, need to note that in electrostatics, we do not have any magnetic vector potential. So the change of magnetic vector potential is equal to 0. And you will agree with me that if instead of writing phi, we had written V, which we are used to, we would have reverted back to our scenario in electrostatics, which is E is equal to minus grad V. But now I have a phi here, so it is the one I'm going to write. So, when a current in the circuit changes, an EMF is induced in the circuit. In such a way as to oppose the change caused in it. So this implies that the induced EMF in such a coil, okay, how it happens, if I can elaborate on this, is that if you have a coil and this coil is connected, for example, to if we have a switch here, or if I can put a switch like this, and you have a bulb, and you try to switch on and off. If you switched on, by the nature of the, if I can try to show that the coil is going to the other side, show that it is entering the other side, I show that it is on top. So I will have the current moving in this direction and goes and finishes by this and here like this. So I can basically try to do this, so the field will be in this direction. So I have the field that will be created will be in this direction. Those of you who are keen, when you switch on lights, or when a car switches on lights and switches off, they do not go off like I switch if I switched off these tubes. You will see them being bright and then they shy away, smoothly. So it means the current is trying to move away and the current is coming. So when you switch on off, it means you switch on, the field is in this direction. When you switch off, there is a change in field. And in the same coil, you are able to get an induced EMF, which EMF would be directly proportional to the rate of change of the current with time. And of course, this change is in such a way as to oppose this current is, this induced EMF is in a direction as to oppose the change caused in it. We agree with that. So it is negative. Or we can say induced EMF is equal to minus L di, where M is the self-inductance of the circuit. But according to Faraday's law, according to Faraday's law, we say that the induced EMF is equal to integral E dot dl in this conservative field, and this would be the same as minus d phi dt. That is from Faraday's law. Although for self-inductance, we are more interested in acknowledging that the induced EMF is proportional to the change of the current, but this change of the current causes a change in magnetic field thread in the coil. That's why we eventually get to be interested in, resurrecting what Faraday talked about. So in that case, the two should be the same. And if the two are the same, this would imply that then L di dt should be equal to d phi dt. And for that matter, then we would be able to get our dt's going, and then we have L being d phi. Yeah. So this is the definition of self-inductance. On integrating, then we can say that our phi is equal to Li. So the constant L only depends on the geometry of the circuit and is called the self-inductance. The units of
Please try again. Thank you.
So consider two neighboring circuits. One and two, in which maybe before I really go on with the write-ups, I need to draw something that, because unlike in electricity and magnetism where I drew these, in this course, being that it is like a repeat, I did draw this, so I should be able to show you that if I had a coil, okay, and I put a galvanometer on this point, and I put another coil in the neighborhood, where I have the switch and the barrel. Of course, if we change the magnetic field in this coil, we are likely to change the magnetic field threading this other coil. And we shall be able to get a hit on this galvanometer. In some other literature, you'll find, or in electricity and magnetism, we drew a coil in this nature and put our galvanometer, you can say G here, and we had another coil where we had our current and switch on this other side. This is the same thing. You make the current go through here in this direction, so you are having this current, and you have a field which crosses to the other one, and if you make this field change, you create a change in magnetic field in the other coil, and you produce an EMF, the principle of the transformer. So this is like what we call the transformer effect. So we consider two neighboring circuits, 1 and 2. You can use this setup or this setup above, in which currents I1 and I2 respectively may flow. Now when current I1, I2, when current I2 in circuit 2, changes, we've already said that an EMF is induced. An EMF is induced in circuit 1. such that we have that the nice E1 is equal to M21 minus the I2 the IT. Well, the bottom line is that we are saying that the induced EMF, assuming this was 2 and this is 1, and we say that the change of current in 2, so if I2 changes, then its field would create a current in 1. Okay? And the EMF E1 induced in 1 would be equal to minus the mutual inductance of 2 on 1. Okay? Then the I2, because it is 2, I2 which is changing with time. Okay? And this is what we are getting on this point. Otherwise, we would have started by saying it's directly proportional and acts in a direction as proposed. And that's why we are coming up with the mutual inductance M21. Now, if the current, it is not one direction. That's why ladies always want equal rights. Nowadays, those who work, they say, I can also bring supper. And so it's a two-way traffic. So being a two-way traffic, if it is happening in one, if the current I1 in circuit 1, a disclaimer, ladies, I use this for the purpose of demonstration, not to hurt your feelings, okay? Or not to appraise your feelings. This is purely for demonstration purposes. When I mentioned you in relation to the course, that is my disclaimer. If then the current in 1 is the one which is changing, an EMF is induced. An EMF is induced in circuit 2 such that now the EMF induced in 2. So if the change is happening up there, if we swapped the current and the switch to be this way and we put the galvanometer this way, then we would be able to have the E2 being the same as minus M. So we are saying 1, the field created by circuit 1 on 2, and then the I1 dt. Of course, because the mutual inductance depends on the geometry, the effect, whether the quarrel has been initiated by the wife or by the husband, the neighbors will say there was a quarrel in their family. They don't care who started the quarrel or who is quarreling more. And for that matter, we say that the constant M21 is equal to M12 is equal to this M is called the mutual inductance. We, however, note that from Faraday's law, the E1 of the EMF in coil 1 due to the change of current in coil 2 should have been actually, watch this, I've wrapped it, but watch this. If it was according to Faraday's law, if we had this as our galvanometer, and we had this as our change in field. Watch this. This is 2, this is 1. We are talking of E1, we are talking of I1, we are talking of I2. That means when we start changing the current here, we are changing the field into. Okay? Because one is idle, it doesn't have anything at the beginning. It is until when we start changing that we result into an EMF induced here and result in a current flow. Similarly, that means we would have this being minus the change of the flux of 1 with the time. So when we change the current here, it produced the field, and this field now we can't be concerned of the field which is within here. We are now looking at the change in field which is in coil 1, and that's why we talk of flux phi 1 in relation to 1. And then we shall also say that of course this would be equal to minus M21 di2 dt, and this would imply that our M21 would be equal to the phi 1 dt times, if I make this the subject, the dt's go, so I would have the phi 1 dt, and then dt, the I1, and therefore I would have that my M21 is equal to the phi 1 the I2. This is the I2. So the I2 there. This is 2, 1. Of course, what I have done for relating the induced EMF E1 in relation to mutual inductance and in relation to Faraday's law, I can do the same with the induced EMF in coil 2. Similarly, nice E2 is equal to minus d phi 2 dt, which is equal to minus M12 di 1 dt, implying that making M12 the subject would be equal to d phi 2 di 1. Thus, I will have that M12 is equal to the phi 2 the I1. We have successfully understood or worked on the concept of self-induction, mutual induction. There?
Why did you consider the self-induction as well as the mutual induction?
Well, at this point,
that's the way we change. That's the current changing in coil.
no, we tended to be interested more in what we are producing in the secondary coil than what is taking place in the primary coil. That is, on the section of mutual inductance, we are more interested on the secondary coil than the first coil. Of course, there is self-induction in the first coil. That's why when you look at a transformer, as you get the field moving through the iron core, the iron core itself is induced, the EMF is induced within a current flows through, which we call eddy currents. But to cut them off, that's why we use laminated pieces, so that there can't be a continuous flow of the current. Similarly, because we are tapping from the secondary, then we don't care about the self-inductance that happens in the primary. But of course, this self-inductance which happens in the primary is one of the causes of the heating of the transformer, power losses, mentioning. Just like we know that the back EMF is responsible for a lot of drag in most of the motors. The drag which happens in the mechanical systems due to lack of lubrication, instead in electrical systems is caused by back EMF. And that's where we lose a lot of energy in trying to overcome your own EMF. If you see when you switch on your fan, how many of you have fans? It doesn't start by being quick. You see it resist here at the start. And that resistance is because of the back EMF until when the buildup is high that it can now run at a constant speed. Yeah, he has put it. He has put, and you can see how long it is taking. You can see how long it is taking to pick up. That is because of because the current is already flowing, but it is taking long to pick up the speed. Even if you put it at full, it cannot start being full immediately. Thank you very much. So I think with that kind of demonstration, which is freely available, you realize that. And credit goes to Buka that instead of me asking who has a fan and some guys bragging that they have pressure in the rooms in form of a fan, he reminded us that we have the fans here. So with that, I think we made